Good morning, everyone. Today is the third lecture of the Principles module, and today we're going to be talking about temperature. And I want to make a note that the next three lectures are connected to one another. Temperature, salinity, and density sort of all go together. But before we get into temperature, let's talk a little bit about water. Water is a really unique substance, and it has sort of a fascinating set of thermal properties. Just the fact that water exists as solid, liquid, and gas at Earth's surface is kind of incredible. Water doesn't behave like other molecules, and it doesn't behave like molecules that are close to it on the periodic table. And because of this, because it exists in solid, liquid, and gas forms, is basically the main reason we can have life on Earth. And as a result of water's special thermal properties, it plays a huge influence on Earth's heat budget and moving heat around the planet. So water exists as a solid, liquid, and gas. And here, this is an interesting way of looking at the three states of matter. So on the left, we have water molecules in ice. And so here, the water molecules, and so the way this is represented in the H2O is the red in the middle is the oxygen. And then the two white spheres are the hydrogen. So it's like this, oxygen to hydrogen, oxygen to hydrogen. And that's the shape that a water molecule takes. It's not linear. Okay, you might expect a typical molecule, something similar to water, would look like this. It would have a linear construction, but it doesn't. It has this bent construction. And so the oxygens and the hydrogens are covalently bonded to one another. But what ends up happening is you have this slight charge because of the way water is set up. So you have this slight negative here by the oxygen and this slight positive by the hydrogens. And what ends up happening is the positive side of the hydrogens are attracted to the negative side of the oxygen. And you can see it sets up what we call hydrogen bonding here. And so this crystalline structure of water is actually quite strong because you have these hydrogen bonds here that are holding these water molecules together in this somewhat rigid structure. And so that's what water looks like in ice. And so if you want to melt that ice, you need to add energy to break these hydrogen bonds, okay, so that the water molecules can start sliding around one another. And that's when you get to here. This is what liquid water looks like, where the molecules aren't regularly oriented. They're sliding around, so you've had to add some heat to do this melting process. But still, there's some attractive forces here. The hydrogen bonding is still happening, where these molecules are more stuck together than a different liquid would be. And so if you want to move from the liquid state to the gas phase, you have to add heat again. And so that's where you evaporate or you boil water. And one of the things that's indicative of the gaseous state is that these molecules are completely independent of one another. You've completely broken all of these hydrogen bonds, and you've gone all the way into the gas state. So in order to move the other direction, of course, you need to remove heat. And so you can condense gas back to liquid, and then you can freeze liquid back to solid. And there's a couple of interesting properties here to keep in mind. So one is that because of this really regular structure of ice, it's actually less dense than water. And it turns out this is really important because on the planet Earth, if ice were more dense than water, then what would happen is you'd have some ice freezing at the surface of the ocean. And then if it were more dense than water, it would sink. And then that would keep happening. And eventually, lakes, this would happen really quickly. You'd basically have frozen ice lakes. You would never be able to have liquid water remaining. And so if water didn't have this special property because of the hydrogen bonding, then we would basically have a frozen over planet a long time ago. And that sort of would have been the end of everything. So these van der Waals forces are a little bit different than hydrogen bonds, so it's worth talking about them here briefly. So van der Waals forces all molecules experience, not just water. And this is a relatively weak interaction when molecules are close together. So water has van der Waals forces, and it has hydrogen bonding. And you have to add energy to water or to any substance for these molecules to overcome these attractions. But the thing with water is you have to keep adding energy. And so before we go too far, just to define a couple of things, because it's a little bit confusing what the difference is between heat and temperature. So heat And we're going to talk a lot about heat, transfer of heat, evaporation, the sort of loss of heat, gain of heat. So heat is the transfer of both kinetic and potential energy from one object to another due to temperature differences. Whereas temperature is just a measure of the average kinetic energy of molecules in a substance. And so it's much easier to talk about, the temperature is X, Y, or Z. Whereas with heat, we're talking about heat lost and heat gained. And then a calorie is the amount of heat needed to raise the temperature of 1 gram of water by 1 degree Celsius. And so when you think about, if you're thinking about food right now, because it says calorie, those calories are a little bit different. It's actually, when it comes to food, I think 1 calorie is really more like 1,000 calories by this definition. But try to sort of separate snacks from your mind here and think about calorie in the physical chemistry sense of the word. Okay, so other cool things about water, because it has these van der Waals forces and hydrogen bonding. If you look on this little chart, it shows the melting point and the boiling point of water as compared to a really similar compound. So if you guys think about the periodic table, one of the things you learn in chemistry is that things that are near to one another on the periodic table, they tend to behave similarly. And that is true, except for water completely breaks the mold. So the melting point of a compound similar to water would be minus 90 degrees C, and the boiling point would be minus 68 degrees C. So if water behaved like these compounds, it basically would never exist as ice or liquid on the planet. It would be stuck always in the gas state. And so here you can see the melting point, or the freezing point. I think it's easier to think of it as the freezing point. So this melting point is equal to the freezing point, is 0 degrees C. So it takes, to get that solid ice to melt, you have to add a lot more energy to it than this compound. And the reason you have to keep adding energy to get to 0 degrees Celsius, or keep adding heat in this case, is because of those special connections. So that ice has those hydrogen bonds. They're really oriented. They want to stay in that position. And so it takes a lot of energy to break them down. And then similarly, when you want to boil water, you have that liquid. So the hydrogen bonds aren't quite as strong in the liquid, and the molecules are moving around one another. But still, nevertheless, you have all those forces you have to overcome before you completely break all those bonds and can generate gas. And so water has these really unusual, super high boiling points and freezing points as compared to what you might expect. Another thing that's related to this is what's called the heat capacity, or the specific heat. And you can see water up here has the highest specific heat capacity as compared to all of these other substances. And so this is the amount of heat required to raise the temperature of 1 gram of any substance by 1 degree C. And you can see here the way this scale has been derived. It's sort of been done in a way to set water at 1. So 1 calorie per gram per degree C. So what a high heat capacity means essentially is that it can take or lose a lot of heat without changing temperature. So if you think about boiling a pot of water on the stove, you put the pot on the stove, you turn on the heat, it's filled with water. That pan, the pot itself, gets hot fairly quickly. But even when the pot is way too hot to touch, if you stick your finger in the water hasn't really gotten that hot. And that's because water has a high heat capacity. So you can pump a lot of energy and a lot of heat into water before you actually start raising its temperature, as compared to whatever it is your pot's made of, with some sort of metal down here. And this is related to water's latent heat. Water has very high latent heat, meaning that it takes a lot of energy to change state. But when you do change that state, meaning go from ice to liquid or liquid to vapor, you release or gain a lot of energy. So what does this look like here? So if you start down here and you have a bit of ice, okay, you add 20 calories, and this is now your unit of energy here, your unit of heat. By adding 20 calories, you bring that ice from a temperature of minus 40 degrees C to 0 degrees C. But it doesn't yet convert to a liquid, all right? And when you keep adding energy, so you add another 80 calories, you don't actually raise the temperature of that at all. It takes that additional 80 calories to break the bonds and convert it to a liquid, Okay, so that's where that high specific heat comes in, where you're pumping energy in, but you're not raising the temperature, you're just breaking bonds, and then now finally you've got liquid. So once you're at the liquid, you add another 100 calories, and at that point you're raising the temperature of that liquid water from 0 to 100 degrees C. All right, so now you've added 200 calories total, and you keep pumping energy in, but you're not raising the temperature. All you're doing is breaking hydrogen bonds, and then bam, you have to add another something like 500 extra calories to actually convert to a gas where you can then start raising the temperature again. All right. So this makes water pretty special, and it's also a pretty useful thing because all of this heat that water can absorb, it can also then eventually release. And so the latent heat of melting is the energy needed to break those intermolecular bonds that hold water molecules rigidly in place in ice crystals. So that's your latent heat of melting. The latent heat of vaporization is how much you need to add at the boiling point to break all those bonds. Remember, because of gas, all those molecules are completely independent of one another, and that's a big number. You have to break all those hydrogen bonds. So it takes, these latent heat values are really big. And then the latent heat of evaporation is conversion of liquid to a gas, and this is below the boiling point, okay? So here then are your other definitions for your latent heat of condensation and your latent heat of freezing. But let's sort of, again, to reflect on why we have these special properties. So this is what your water molecules look like in a solid. Nice and rigidly put together in a three-dimensional structure. With liquid, you've broken some of these bonds, all right, and they're sliding around one another. And then in the gaseous state, they're all completely independent of one another. So all of these special properties of water play a big role in climate. And so it helps moderate the temperature on Earth's surface so that we don't have oceans in near the equator where they get lots of sunshine, where they're not like rolling and boiling, right? The ocean can take that heat and it doesn't necessarily raise the temperature immediately. And likewise in the polar oceans where it's really cold, thankfully they don't freeze solid. And so this energy is exchanged across the Earth through evaporation and condensation cycles. And it keeps Earth a nice habitable planet for humans and other things. So in the low latitudes, you have the ocean, it's warming, right? So you have the equator here, it's getting heat from the sun. And what ends up happening is that you end up with evaporation of the water. And so then the heat that you've now, and remember, evaporating makes things cooler. Think about the fact that when you sweat on a hot day, the water on your body evaporates and it leaves you feeling cooler behind. So this evaporation process is basically like the low latitude ocean sweating because it's really hot from all the sunshine. And so those gas molecules go up into the atmosphere and they're transported, which we'll learn about when we get to atmospheric circulation, but they're transported to the higher latitudes towards the poles. And what happens at the poles is it ends up raining. This gaseous water vapor is released as precipitation, and precipitation falls down onto that, and precipitation is where it releases that heat. So it takes the heat from the low latitude ocean, brings it to the higher latitude ocean, and then it deposits some of that heat on the high latitude ocean. And it's these evaporation and precipitation, this heat that's released and then reabsorbed is related to these special properties of water. And this is known as the global thermostatic effect. So the marine effect is that the oceans basically moderate temperature. And in addition to doing this regionally, where they take heat and move it to the poles, they also do this from day to night and during different seasons. And so I think the easiest way to see that is here. So this plot is showing day and night temperature differences. So think about the ocean. If you think about the daytime temperature minus the nighttime temperature, they're actually not that different. There's a minimal change from day to night. It's a little bit cooler, maybe during the night than the day, but it's not, significant. For the most part, it's the same. And so for example, if you're ever at the beach and you go out to the ocean water, it's not like the water, the ocean water in Cape Town changes from 25, 30 degrees in the afternoon to 15 or 10 degrees at night. That's what we experience in the atmosphere, but that's not what's happening to the ocean. And that's again because you have this large body of water, and you're adding a bunch of sunshine to it during the day, but it can absorb a lot of energy without changing temperature, right? So it absorbs energy and changes temperature, and then you've got this long flat part. And so you think of the ocean as doing this. So the sun's shining on it all day and it's absorbing energy, but it's not changing temperature. But the land isn't like that, right? The land, think about something like a desert. It gets really hot during the day, and then the sunshine goes away and it immediately gets really cold, downright freezing at night in some places. And that's true. Like I said, think about the daytime, nighttime swings in temperature we experience from the atmosphere. They're really big compared to what the ocean is experiencing, which is basically almost no change in temperature day to night. And again, this is because of the special properties of water that allow it to absorb all that energy, and the energy goes to breaking bonds, but not to actually raising the temperature. So moving from thinking about special properties of water to what temperature actually looks like in the ocean, we know a lot about sea surface temperature, which is usually denoted by SST from satellites. And this is a satellite image of sea surface temperature from January, so that'd be summer in the southern hemisphere. And you can see the color bar here. So this is pretty typical. So surface ocean temperatures range from about -2 degrees C to about 32, 33 degrees C. And you can see there's a strong latitudinal gradient. So we've got cold water here at the poles, and then getting warmer as you move towards the equator in both hemispheres. Okay, sort of as you might expect based on solar insolation. But this is the surface. So then thinking about, all right, well, let's go deep into the ocean. So on the left, we have a depth plot. So now we're in one spot in the ocean, and we're looking from the surface all the way down to 4,000 meters. And here we have temperature from 0 to 20 degrees C. And so what you can see, so this is a region where the surface waters are 20 degrees C, so pretty warm. But if you go just down a little bit, you hit what's called this thermocline. And the thermocline region is defined as an area of the ocean where you have a rapid change of temperature with depth. So let's say this is about from 500 meters to about 100 meters. You've gone from just under 20 degrees C to just under 4 degrees C. So that's where this thermo and cline comes from. Cline you can think of as rapid change, thermo as temperature. So from about 500 meters or 700 meters on down, the ocean's quite cold, so under 5 degrees C. And if you ever see something that says, what's the average temperature of the ocean, it's going to be something like 4 degrees C. Because if you think about the volume of all this water, right, 4,000 meters deep worth of water, it's all 4 degrees C. Whereas this little bit of surface water is warm. And of course, this temperature profile is going to change dramatically depending on where you are in the ocean. So the example on the left is pretty typical of, let's say, a mid-latitude spot. So if we're looking at the plot here on the right, this is your green where you've got your mid-latitudes where it's warm at the surface, and then you've got your thermocline and it drops the colder. If you look at the tropical ocean, which is in red, it's a lot warmer at the surface, but there's still this dramatic thermocline. So by the time you hit 500 meters, it doesn't matter how warm it was at the surface. You've hit now this colder deep water. And then when we look at the polar waters, they're cold at the surface and cold at the deep. So they've basically got no thermocline. It's basically a straight line. And we call this isothermal. Iso meaning it doesn't change. So isothermal. And that's the blue one, the polar one. So generally speaking, greater than 1,000 meters, regardless of where you are in the ocean, the temperatures are pretty uniformly low. The vertical temperature profile in the high latitudes is essentially a straight line. It's a vertical straight line, so that's your high latitude temperature profile. Whereas in the middle latitudes or the low latitudes, or the subtropics or the tropics, you have this warm layer of water at the surface, and then it gets cold below. And we call this warm layer the mixed layer. And this depth of the mixed layer can vary anywhere from 20 to 500 meters. And the mid-latitudes will have, now introducing another sort of layer here, the mid-latitudes will have some seasonality. So the high latitudes will look like this all the time regardless. And the tropics will basically look like this all the time regardless. Warm at the surface, going down to cold at depth. But the mid-latitudes, this temperature distribution sort of with depth will change seasonally. Because what happens in the mid-latitudes is there's a lot of seasonality in atmospheric temperature. And so the mid-latitudes will have a thermocline that looks like this in summer. So it'll be warmer and then it'll get colder. And then in the winter, it'll actually cool off a little bit and it'll look more like this. Whereas the tropics sort of look the same and the high latitudes look the same regardless of seasonality. And this is data from EWOS. So this is a temperature cross-section. So we're going to look at plots like this throughout the course, looking at different types of parameters. And the first thing to do when you see something like this is to find the map here that shows you where on Earth you're looking. So this shows you that you're in the South Atlantic, okay? And this line is going from the east coast of South America to the west coast of Africa. And this is basically a slice right across the ocean. So you're looking here at, this is the surface and this is depth. And it's basically, so here you're leaving the coast of South America and you're marching across to the coast of Africa, and you can even see that here on the bathymetry, and we'll get to our bathymetry lectures soon, where this gray is showing you that the ocean is sort of shallow here, it gets deep, and then you hit your mid-Atlantic ridge here, and then again you're approaching the coast here. And now this is temperature with our color bar here. So we've got our surface temperatures are quite warm, as you might expect, because this is a tropical region, I would say, maybe sort of a little bit subtropical, but pretty close to the equator here. So all your surface waters are warm, but then you hit that 500 meters and they start to get colder, as you might expect, and then down from about 1,000 meters on down, nothing's warmer than 4 degrees C. And what's interesting here is you see that there's actually gets colder again over in here, on down. And when we talk about water masses, you'll learn about why this is, why there's some different water masses here. But this is pretty typical of a temperature cross-section. So imagine if you were to draw a profile for a given place. So let's say you were asked to draw a profile here, like we saw on the previous slide, and you had depth as a function of temperature. It would look something like this, really warm, and then it rapidly gets really cold and then goes down and is cold all the way, right? So you would say that this was maybe, I don't know, it's sort of hard to tell, 20 degrees C. And then as you move down, by just under 1,000 meters, you've hit 5, and 1,000 meters, you've hit about 4 degrees C. So here you would say that's 4 degrees C, and this would be about 1,000 meters. Okay, so this plot is related to this plot. So by looking at something like this, a cross-section, you should be able to draw for any given area what the depth profiles look like. Okay, so that's the end